Hey, welcome to AP Chemistry. You're here with Mrs. Mays, and today we're going to talk about communicating your results in a scientific way. So push pause right now and get your graphing calculator out before we go any further. Do it. Push pause. Don't wait. Got it? Okay. So first we're going to start with every measurement we make is going to have some uncertainty built in. It's the basis for where significant figures come from. So if I'm going to measure the volume of something in a beaker, it's not going to be the same as measuring the volume of something in a graduated cylinder. Both of them have some built-in error. All measurements are uncertain to some degree. It just so happens, though, that for this instrument, the beaker, the uncertainty is going to be much larger than in a graduated cylinder. Notice how much closer the markings are and how much more precise you can be with a graduated cylinder. That's why we don't use beakers to measure volume. Now here's a close-up picture of two different burettes, and I want to point out again the limits to which our measurements could be accurate. See, in the one with the most markings, you're accurate to 0.05. It's saying, well, we know it's 10.25, but that 0.25 is because it's like halfway, well, less than halfway to halfway, right? So we have to make our best guess. We know that it could be maybe 10.30 or it could be 10.20, but the best we can do is to within 0.05 milliliters. On the other hand, if we're guessing here between, let's see, what would this be? Burettes measure sort of upside down. So here's 10 and here's 11, so we would call this 10.5, right? And what's about halfway in between? Well, we could say 10.25 if we had more markings here, but we don't. You can only guess one marking past what is given to you. So we can't put a 0.25. And now our uncertainty becomes a little bit greater. Instead of knowing to the precision of the 0.05 mark, we could be off by 0.3. So consider, like, how much wiggle room does your measurement give you? And every measurement that you write in my class, I want you to write exactly like this has been written, where you write down the measurement and give the uncertainty of that instrument. How much is that estimation likely to be off? All of your measurements need to have the uncertainty built in, because I need you to think about not just how many sig figs to use in your answer, but where those sig figs actually come from. And you have to decide by looking at the instrument you use. Then once we get all of our data, we'll be looking for trends in our data. One trend is called precision. It describes how repeatable the results have been in your measurements. We report precision in this class as standard deviation. There's some other ways to describe precision, but standard deviation is the one that we're going to use here. So you could see in this picture with the target, all of the arrows have sort of landed in the same spot. So we have very precise values. But since we're not really hitting the bullseye, the values are not accurate. So accuracy is the way we would describe how close your measurements are to the true value or the accepted value. So we report accuracy as percent error. And then to improve the accuracy, we often use the mean, right? We take several measurements and find the average, the mean of those numbers, and that helps to improve our accuracy. Errors, really, though, are measurement discrepancies. Errors are not the same thing as mistakes in your lab. An error simply means that you have a discrepancy in your measurement. There are a couple of types of errors. One is just a random error where there's an equal chance of that measurement being either too high or too low. Random errors are addressed by doing multiple trials so that you sort of balance out the ones that are too high with the ones that are too low. We expect these types of errors to occur, and we address those by doing more than one trial. Systematic errors, though, are errors that are going in the same direction each time. For instance, if your scale is not calibrated that could create a systematic error. And so we want to avoid this by calibrating the instrument before we use it. That's one of the easiest ways, right? Or fixing your mistakes. If you know that there's something off about your measurements, go back and redo, because mistakes are not errors. You messed up, go back and fix it. Don't put in your conclusion of your lab report, we made a mistake. Well, no, that's not acceptable. That's not an error. An error is a measurement discrepancy. If you're not going to be precise in your measurements, then you're not going to be accurate in your measurements either. So fix your mistakes and redo the things that you need to redo. And then we'll have meaningful discussions about measurement discrepancies in your lab report, rather than just a discussion of all the ways you messed up. Now let's look at a data set. Suppose that you actually have a bunch of data. So in your note-taking guide, you have a list of numbers to enter. So now's the time when I want you to get your graphing calculator out, and I'm going to take you through the steps of how to enter this data set into a list. This is a data set maybe you've seen before. So first we want to click the button that says Stat, because that's where we're going to do all of our statistical analysis of data. And then push Edit, and we should have the ability, there we go, I have an empty list. So let's enter the numbers from the data table into your calculator. So just type them in as they are on your paper. Don't worry about how many sig figs, because these are real data from the hydrates lab experiment from last year's class. There, I fixed my mistake. Check all your numbers to make sure that they match the data table, and also check that you've entered 10 values and not skipped any or entered them twice. So double check the accuracy of your data, and then we're going to do something with it. So what happens next is that we're going to analyze our data. By the way, if you're using an Inspire calculator, then you're kind of on your own. I have limited experience with the Inspire, but I do know that you can enter your data in a column by going to first Lists and Spreadsheets, and then just enter your data in a column. Now we're going to use a technique called one-var stats, or univariate stats. So the first thing you have to do is turn on diagnostics in your calculator, or it won't even do any good. So do second 0 to get your catalog, which automatically puts you in this realm of alphabetical stuff here. See, the A is highlighted. So now that we've got alphabet, choose letter D for diagnostics. There's D, and then arrow down till you get to diagnostics and find it where it says diagnostics on. Push enter, and then it's saying, hey, you want to do this? And I say, yes, please. So push enter again, and it says done. So now our diagnostics are turned on. Our next step is to go to stat again. Sorry, this calculator is in the way of what we're trying to do. So go to stat again, choose calc, then one var stat, univariate stats. And from there, we just have to tell it which list to evaluate. So push stat, and then arrow across to calc. My first choice is one var stats, that's the one I want. Now I have to tell it which list. I put my data into list 1, so I do second and the number 1, because in the little blue letters it says L1 above the number 1. So now I've evaluated list 1 using univariate stats. So what do all these numbers mean? Oh, let me show you what to do. If you have the TI Inspire, press menu and then statistics, wherever it is. On my calculator was option 4. Option 1 on my Inspire app is stat calculations, and then choose the one variable statistics. So you should find something similar. Now if you have a Casio calculator or HP, I don't have any experience with those whatsoever. You're kind of on your own. Sorry. It's the best I can do. All right, let's figure out what all of this means. So X bar is the mean. That's where we take all the numbers, add them together, and then divide by how many numbers there are. You've been doing averages for a long time, so you all know how to do the mean. Sigma X, capital Sigma X, is the sum of all values, where we just added them all together. And this is going to be useful to us to help find the mean, for instance, and other things. Sigma x squared, though, is where first you square the values and then add them together. So it's the sum of the squares. And we'll use that occasionally if sign is an issue. We don't want to know if it's positive or negative. We just want to know what the absolute value is. Then squaring a number gets rid of signs, doesn't it? Sx is the standard deviation calculation that we get to use. Oops. It's the standard deviation calculation that we get to use when our sample size is less than 10. But sigma x, lowercase sigma x, is the standard deviation that we use when the sample size is greater than 10, where n represents your sample size. How many numbers are in your data set? So that's called sample size. Sometimes in science we call this trials. How many replicate trials did you complete, measuring the same value? And that's an important thing. The more you do, the more accurate types of calculations we're able to do. All right, min x is your least value, the smallest number, minimum, right? Q1 is your lower quartile. When you were in 6th grade or so, you probably did box and whisker plots for the first time, and you ranked all your numbers from least to greatest and cut it in half, and that's where you found the median, right? The middle number in your data set. And then you cut your lower half in half for the lower quartile, and your upper half cut in half to find Q3, your upper quartile. And then you plot it on a box and whisker plot to see the spread of your data so that you can decide, are there outliers or not? And that's what we're kind of looking for. Are any of our numbers so far away from the average that they're considered to be unreliable? The last value, max x, is just your greatest value, the maximum. That's what max x stands for. So this all kind of looks like Greek at first because, well, quite frankly, it is. Oh, you didn't see all of these numbers? You only saw down to n? Just arrow down on your calculator. They're all there. See, there's the rest. Arrow back up to see the ones you had before, because now we're going to use them. We're going to use these numbers. The empirical rule gives us the ability to justify using standard deviation as a means of evaluating the precision and choosing testing for outliers. See, in any data set, 68% of the data lies within one standard deviation of your mean. That means a smaller spread. But if we widen the spread to 2 standard deviations, that should give us 95% of the data. Anything that's beyond that might be too far from the average to be counted as reliable data. And then 99.7% lies within 3 standard deviations. Here's what that looks like in the bell curve. This should look a lot like the activity we did in class called faux fish figuring, where we went fishing and measured the weights of the fish. All of the curves that we generated as a class kind of looked like this shape. And we're going for this part, where all of our data should be within 95%. 95% is like making an A, right? So this is the section that we're going to evaluate. Anything that's sort of on the fringes, either too high or too low, we're going to cast that out as unreliable data. So we're going to check for outliers by applying the 95% rule. We take the mean, x bar, and we add 2 times the standard deviation. And in our sample, we get to use sigma x because we had 10 samples. And then we add, and that will give us our highest acceptable value. Anything bigger than that number, we don't get to keep because it would not be reliable. And then to find the lowest acceptable value, we subtract 2 times the standard deviation from the mean. That will give us our lowest acceptable value, and any number that's lower than that, we might want to cast out because it doesn't fit the pattern of our data. It's not precise enough to be included. So let's do this with our real numbers. And I want you to think about that list we just put in. In the list that we just entered, did any of the numbers seem a little bit off to you? They did to me. Let's look at them more closely. So we'll take our mean, which is 0.41386, and add to it 2 times sigma x, 0.0870, 0.0871, we could say. We'll worry about sig figs a little more in a little bit. And let's find the lowest value. So we take our mean, which is still 0.41386, oops, and subtract. It's 2 times the standard deviation, 0.0871. You can put in your calculator as many digits as you like to. You just don't have to write it on your paper. So let's see what's the highest value we can keep. So 0.41, where did it go? 386 plus 2 times 0.0871. So the highest number we can keep would be 0.58806. Anything higher than that number would be considered unreliable, and we would toss it out and get rid of it. Let's look to see the lowest value that we could keep. 0.41386 is still the mean. And this time we're going to subtract the standard deviation, 0.0871. And that gives us this lowest value of 0.23966. So our question then is, did we have anything in our data set that doesn't seem to fit the pattern? Is there something that's unacceptably far from the mean? So go back to stat, and let's look at our list of numbers. And we're going to look for anything higher than 0.58806. And I see 0.55. Do we have anything higher than that? I didn't see anything higher than 0.55. So as far as the upper limit is concerned, we're okay. But look at the very last digit, the 0.19. That's lower than our lowest acceptable value of 0.239. So we had a 0.19 that's not big enough to fit in our data set. So what do? Well, it's pretty simple. I said we were going to cast it out, just like Survivor. We're going to vote that guy off the island, and now it's gone. But we'll have more reliable data because that outlier, the number that doesn't fit the pattern, is gone. So now in my lab report, rather than putting the first average in my report, I have a better average to give now and a better measure of precision. So when I report the mass of water that left the hydrate, I get to use this 0.438733333 plus or minus my standard deviation. Now I'm going to use Sx instead of sigma x, 0.05. And that's in, let's see, how many sig figs? I'm going to put a few more and then let's decide sig figs. Okay, let's look at the data from the data table. All of the students reported measurements to 4 decimal places except for, oh, here's 3 and then here's 2. So because of these values that students in your class reported to us, we can't be any more precise than 2 decimal places. So in all of your reports in the calculations that you do, you're restricted to only 2 decimal places. Don't be the student who restricts our sig figs. If you get 0.41 exactly and your balance goes to 4 decimal places, fill in the zeros, keep the zeros there, and don't drop those away, because your classmates are relying on you to give us the most possible number of sig figs. And when we use an analytical balance, that's going to be 4 decimal places. So don't you be the student that creates problems for everybody else. In this calculation, we're restricted to 2 sig figs. So this number changes to 0.44, and then 2 decimal places out gives me a plus or minus of 0.05. And that was in grams. So this is how we'll be reporting data in the conclusion of your lab report, so that you can tell me what it actually means. What do your results mean in the first place? Okay, let's look at where to put this in your lab report. So in your lab notebook, you'll be using the right side of the page, the right-hand side of your notebook, to write your lab report and record the data. Use the left side of the page to show calculations, graphs, and statistical analysis. This is also where you're going to write detailed observations. Will be on the left side of the page. Notes that you think may or may not be pertinent, but you want to write them down just in case they influence your data. Those all go on the left side of the page. The right side of the page is the formal lab report that I'm going to be grading and evaluating to see if you're actually understanding. So let me show you what this would look like in a student lab report. Here's the side where they have the written report, and then here's the side where they're making notes and doing calculations and stuff. So that's how we're going to divide your lab report. If you forget and you just continue writing on the back of your page by accident, don't worry, I'm not going to take off points the first time, but I might the second. So that's how to communicate your results. We'll do more statistics in class so that you get the hang of this.